Welcome to another video in our aerospace tutorial series on Estimate Aircraft Performance with Aircraft Performance Analyzer live task. You can download this live task from File Exchange or GitHub or add it directly from add-ons in MATLAB. In this video, we will learn why we need to estimate aircraft performance and how it helps us in the conceptual aircraft design. Moving forward, we will learn how we can use Aircraft Performance Analyzer live task to estimate various performance parameters including takeoff, landing, climbing, and various important speeds. Finally, we will conclude this video with key takeaways. Let's start this video by understanding why we need to estimate aircraft performance. In the last video on constant analysis, we learned how we can convert design requirements into meaningful ratios with the constant analysis live task and select initial parameters for an appropriate wing sizing and power plant. If you have not checked this video yet, please find the link in the description. Based on these initial parameters, other component sizing and their locations are calculated. Depending on the initial choice in the design space, we can have multiple solution aircraft that meet design requirements. To compare these designs, we need to estimate the performance of the given aircraft design. For this purpose, we will use the Aircraft Performance Analyzer live task. Let's move to the MATLAB and explore Aircraft Performance Analyzer live task. You can add this live task either from add-ons in MATLAB or download it from File Exchange. Once the live task is installed, you can add it to the live script from the Insert submenu. API live task includes three major sections: the input section, the choose analysis type section, and the create fixed wing object section. The first section is the input section. It demands various types of data to model aircraft kinematics, including mass and geometry parameters, propulsion parameters, and aerodynamics parameters. Propulsion parameters model electric propulsion system. Aerodynamics parameters include data for lift and drag, including contribution from control surfaces. Finally, atmospheric parameters demand data for latitude, longitude, and altitude. It helps to customize the environmental and gravity parameters. The next section is to choose the analysis type, where you can select from a variety of analysis. Let's explore the power required analysis. After selecting the analysis type, hit the Perform Analysis button. This generates both graphical and numerical results. Graphical results along with important data points are available here. For numerical results, you can find the API structure in the workspace. Along with input data, it also contains a performance substructure that has all the important performance data points. With API live task, you can do multiple performance analysis, including power requirement, range and endurance, takeoff, and landing. Along with performance analysis, you can also create aero.fixedWing object for stability analysis. For this purpose, you can provide detailed aerodynamic parameters in the Create Fixedwing Object section. Here, the data for CD0 and CL0 are pre-populated as per the chosen state. Once you choose the appropriate state, you can export the aero.fixedwing object to API structure in the workspace. You can convert this live task into the code and use it for further custom analysis. Now that we have learned how to estimate aircraft performance with MATLAB, let's explore how can we use the live task to study the impact of various parameters and compare various aircraft configurations. Let's consider a set of aircraft configurations that are identical in all design aspects except for the CLmax value. Our goal is to analyze how changes in the CLmax affect the takeoff ground roll distance. To do this, we will use a for loop to estimate performance for each CLmax value configuration. Since all other parameters remain constant, we can reuse our existing API structure by assigning it to a temporary variable called aircraft. We will modify the CLmax value for each configuration and then estimate its performance. For the performance estimation, we will repurpose the code generated by the API live task and encapsulates it into a custom function. After estimating the performance, we will store the results in a structure that holds data for all configurations. Next, we will plot this data to visualize the results. As shown in the plot, increasing the CLmax value leads to reduction in the takeoff ground roll distance. A configuration with high CLmax value will demand a high cambered wing, which may be complicated to manufacture. Whereas low CLmax value configuration would be easy to manufacture but will result in more ground roll. Depending on the overall design requirements and based on the estimated performance parameters, we can compare and select most suitable configuration for the desired application. Let's move to the key takeaways of this video. In this video, we learned that estimating aircraft performance helps evaluate and compare various solution designs. With API Live Task, we can predict performance for takeoff, landing, climb, drag bucket, and various important speeds. It also provides both graphical and numerical results which can be used further for optimization workflow. We can also create aero.fixedwing objects for aircraft static and dynamic stability analysis. For more information on aero.fixedwing object, please refer to the aerospace toolbox documentation. In case of any queries, please feel free to reach out to us at roboticsarena@mathworks.com. Thank you.